Okay, good morning. I neglected to explain something yesterday, which, so we had box Q, and I sort of matter-of-factly said that inverting this operator is what's called the Debraj-Neumann problem. But I did not explain the terminology Debraj-Neumann. What does that have to do with any Neumann in mathematics? But here's what it is. So for you to be in the domain of box Q, we have, well, first of all, there are the explicit conditions. You should be in the domain of d bar and then intersect domain of d bar star. Of course, being in the domain of d bar is just an integrability condition on the d bar, but this is more. It's a boundary condition, and this is called the explicit boundary condition because for you to even be in the domain of the quadratic form, which defines box Q, you have to have this, right? But then there are implicit conditions, namely, we then found d bar u has to be in the domain of d bar star, and d bar star u in the domain of d bar. Again, here, this is just an integrability condition, but this is a boundary condition. It's implicit because when you just write down the form, the quadratic form, you don't really see it. But then it comes out. So now, what does this mean that d bar u should be in the domain of d bar star? Well, let's take any form, say, what should we call it? Say alpha, summation j, aj, dc j bar. And let's say alpha is, I don't care, continuously differentiable on the closure or something. Then we should have summation j, hak, d rho, dcj equals 0 on the boundary, and this should be for all k. Now, if you take the form whose coefficients are given by this, so that would be a q minus 1 form, then this is what's called the normal component of alpha. And the reason for that is if you change coordinates so that, say, imaginary Wn is the real normal, and then the real part of Wn is tangential, and then here W1 through Wn minus 1 span the complex tangent space. And if you write down the form at a point in these coordinates, then what this does is it'll pick out all the terms that contain a dWn bar. And so that's why it's called the normal component, okay? So then this boundary condition says normal component of d bar u should vanish on the boundary of omega, okay? Now compare this to the Neumann boundary condition for the Dirichlet problem. So if this is the domain, well, the Neumann boundary condition just says that the normal derivative of the function should vanish on the boundary, right? But the normal derivative should vanish on the boundary. I can say gradient h dot the normal should be 0 on the boundary. In other words, the normal component of the gradient should vanish on the boundary, or if instead of the gradient, if you want to phrase it in terms of forms, you take the differential of h, its normal component, then the Neumann boundary condition says the normal component of the differential of h should vanish on the boundary, right? And here, well, instead of d, we have the d bar, and so the normal component of d bar should vanish on the boundary. I believe that is how the terminology D-Neumann problem originated in the sort of late 50s, early 60s. Does that answer your question? Okay. All right. So now, remember we have seen that the box Q can indeed be inverted, has a bounded inverse. The Neumann operator. Now, from the point of view of partial differential equations, of course, one would always like to know regularity properties. That is, if the data have a certain regularity, then will the solution have the same or better or some regularity, right? So one does the same here. And sort of the strongest is subelliptic. Namely, NQ maps, I'm using the WK for the usual L2 subleft spaces, forms with coefficients in subleft K to subleft K plus epsilon for some positive epsilon. Now, the point here is epsilon is in general small. In particular, it's at the maximal possible epsilon is 1. So why is this called subelliptic? Well, NQ inverts an operator, a second order operator, right? So naively, one might guess, well, if you can invert it well, like you were able to do, you should gain 2 derivatives, right? That would be the elliptic situation. Well, that's not the case here. The best you can have here is epsilon equals 1, but you can have smaller epsilon, and just when this happens, that would be material for a whole other lecture series. This is if and only if the domain has a smooth boundary and is of what's called finite type. Roughly, this means the order of contact of complex varieties with the boundary should be bounded above. Another question one might ask is compactness. That simply says that NQ as an operator on L2 is compact. And of course, if you have subelliptic situation, this implies compactness, because if you have this, in particular if K is 0, this means you map L2 into subleft epsilon, which then embeds compactly into L2. Or the next is just sort of the weakest, global regularity. NQ maps forms that are smooth up to the boundary, to forms that are smooth up to the boundary. And it turns out compactness actually implies this. It's not totally obvious, actually. It requires quite some work to give a serious proof, but nonetheless, this is true. Now, like I said, these questions are interesting from the point of view of PDEs, but they're also interesting from the point of view of several complex variables. For example, Well, let's just look at this. Earlier this week, actually, I think yesterday, Bell's condition R appeared. So this was the Bergman projection on function. Recall this can be written as f minus d bar star and 1 d bar f. So if you know that you have this property, then if the function f is smooth up to the boundary, well, it's d bar is smooth up to the boundary, this will be smooth up to the boundary. Here you differentiate. So then you will have that the Bergman projection preserves smoothness up to the boundary. And this property is important, appears in various places. We saw one, but also it's important in the context of holomorphic mappings that Kengo also mentioned. Namely, if you have domains, pseudoconvex, which are biholomorphic and satisfy Bell's condition R, the biholomorphism will extend smoothly to the boundary. There is an interesting question here concerning global regularity. Namely, in all instances where one can establish this, one actually establishes that the subless spaces are preserved. This is weaker, right? So it is an open question whether you can have this, but as one says, with loss of derivatives. In other words, you know, sub fk goes in some sub fk minus something. This is not understood. For general differential operators and inverses, this may happen, but here it's not known. So I will ignore this and this for the rest of the week, and we'll be talking about this. Another subject that's also very interesting that I will ignore. Well, we have self-adjoint operators here, box Q and inverse N, say box Q. So one should look at the spectral theory of these operators. That turns out to be a rich source of interesting problems, and the spectral properties reflect complex geometric properties of the boundary. So for example, well, here we're in the context of pseudoconvex domains, but if we just look at the d-bar Laplacian, you can set that up on any domain without pseudoconvexity and look at the spectrum. And then you can tell from the spectrum whether or not the domain is pseudoconvex. Well, roughly speaking, what you need to have, if the domain is pseudoconvex, the Laplacian should be invertible, right? So the spectrum should stay away from zero. And I mean, it's a little more subtle than that, but just to give a flavor. What's also studied in sort of under this topic is stability of the spectrum when you perturb the domain a little bit. And so that's, I mean, there's a very recent preprint which sort of establishes the stability under certain conditions, which are going to be related to a condition which we're also going to be using here. All right. So now then, going to concentrate on compactness for today and Thursday and Friday. So that's sort of part 3. Of the Neumann operator. Say again. Greater or equal to 0, yes. Yeah, well, you can say something, but it's a little tricky. Yeah, it's not as clean cut. Right. So let's say, yeah, I'm so used to having that. I forgot to write it. Yes. One can exploit certain dualities and so forth, but all right. Well, so one reason why compactness is interesting, other than, you know, if you're an operator theorist, it's interesting by itself. But the other one is here. this was for a long time, this was sort of a main avenue for establishing this. Another reason why it's interesting, it has applications for the Fredholm theory of tuplets operators on the domains. By the way, here I forgot to give some examples. Well, for compactness, we'll see examples the rest of the week. Subellipticity, if you've looked at the handout, the simplest case when the domain is strictly pseudoconvex, then the epsilon here is 1. For global regularity, this is true on large classes of domains, but not on all. And sort of a nice geometrically simple subclass where this is true is when the domain is Euclidean convex. And always I'm assuming smooth boundary in these cases. So when the domain is actually convex in the Euclidean sense, which is stronger than pseudoconvexity, then you have this property with, in fact, preservation of the Sobolev spaces, exact preservation. This is a result that goes back 90s, I suppose, yeah, to Harold Boas and myself. All right, so now compactness. Well, here's a lemma from functional analysis that is very useful in this context, in the context of differential operators and their inverses. So we have capital X, Y, Hilbert spaces over the complex numbers. All my Hilbert spaces are complex numbers. And T is a linear operator from X to Y, linear. Okay. There are two statements in this lemma. The first one is the following. If you have a third Hilbert space, Z a third Hilbert space, a linear map S from X to Z, linear, continuous, and important part, it should be injective. Then if T is compact, oh, let me rephrase it. If T is compact, then for all epsilon positive, there exists a constant C sub epsilon such that the norm of Tx, that's the norm T maps into Y, the norm in Y is less than or equal to epsilon times the norm of the vector X in the space where X lives in X plus some constant, well, this constant, which in general this is going to be big, in the applications epsilon is going to be small, times the norm of Sx. In our applications, typically, a typical application is going to be where S, where X is, say, L2, an L2 space of forms, C is, say, Sobolev minus 1, then the embedding is, of course, injective. So that will be satisfied. And then when we have a compact operator on that L2 space of forms, we have this, where here is going to be C epsilon times the norm in Sobolev 1. Then there is a second statement. So this is sort of a necessary condition for compactness, right? Then the second statement gives a sufficient condition. So it's not quite the reverse of this. You'll see in a moment why. Namely, we assume now there's a little bit more flexibility. Assume that for all epsilon positive, there exists a Hilbert space C sub epsilon, a linear, now compact operator S epsilon from X to C epsilon and a constant C sub epsilon such that the norm of Tx in Y is less than or equal to epsilon times the norm of X plus C epsilon times the norm of S epsilon X in the space C epsilon. Then T is compact. Yes?
The one says that exists that a Hilbert space or for every
Say again?
statement one.
Yeah.
True for, does it say there exists such a Hilbert space or for every Hilbert space?
Yeah, no, C is just any, right, any third Hilbert space, right, any one. If T is compact, you will have that, as long as you're injective here. Now here, actually, I stated this in this generality, even though I think for what we're going to do, we're actually only using a weaker form. Namely, in particular, it's going to happen that the space C epsilon is actually going to be the same for all epsilon. And again, it's typically going to be a sublife minus one space. And then the embedding is going to be from an L2 space into sublife minus one space. Over there, we needed it to be, that it was injective. Over here, we're going to need it that it's compact, which of course it is. And we'll see in a moment how to use this lemma. The proof is a little exercise. That part is fairly straightforward. That part, the easiest way I found to prove it is to make an indirect argument. Assume this doesn't exist, and it leads to a contradiction. All right, so now, with this lemma in hand, we are going to reformulate the condition that NQ be compact. In ways that are useful for either working with the condition on the one hand, or on the other hand, for establishing the condition. So let's make this a proposition. So I'll make a bounded pseudo-convex. The following are equivalent. One, NQ is compact. Two, the embedding JQ from domain of D bar intersect domain D bar star into L20Q is compact. Three, for all epsilon positive, there exists C epsilon such that norm of u squared less than or equal to epsilon d bar u, norm squared plus d bar star u, norm squared plus c epsilon minus 1 norm zero q. And this is u. Well, of course, u should be in the domain of d bar and d bar star. In fact, very often to establish compactness, what one proves is this. Not always. Sometimes one also uses the statement, let's see, this was 3, 4, which I'm about to write down. Make sure I get it correct. Yeah. The canonical solution operators to d bar at 2 consecutive levels, namely d bar star and q, goes from L2 0q. Well, the d bar closed forms, stating L2 0q omega to L2 0q minus 1 omega, and the one level higher, d bar star and q plus 1, kernel d bar sitting inside L2 0q plus 1, to L2 0q. These two are compact. Okay? So, well, let's see. Well, some of the statements here are pretty clear. The equivalence of 1 and 2, this is just because NQ is, remember, it's JQ star composed with JQ. So that's clear. Then the equivalence of 1 and 3, we now use this lemma over there, say, suppose we have this, I'll often say this estimate, even though it's really a family of estimates. And by the way, it's usually this is referred to as a compactness estimate. Again, somewhat incorrectly, it's a whole family. But suppose we have this, then we're going to use the second statement here with z epsilon sub f minus 1 for all epsilon. The space X is going to be domain d bar intersect domain d bar star, right? And embedding, and Y is going to be L2, the 0q. Then S, where is S? This. S epsilon is now just S from domain d bar intersect domain d bar star. This embeds continuously in the L2 and therefore compactly into sub f minus 1. So then the compactness estimate over there just gives this estimate. And so it then says actually that JQ is compact. And we've already seen JQ compact, of course, means NQ compact. And in the other direction, we use the first part of the statement. For this, those of you who looked at the handout have seen this. This follows from what's sometimes called Runge's formula, namely, one can express NQ in terms of these solution operators in the following way. it's d bar star nq star d bar star nq plus d bar star nq plus 1 times its adjoint. Improving this formula is not particularly hard. It's a little acrobatics with playing around with box and so forth. Well, so then obviously, if these two guys are if we have these two guys compact, this is going to be compact. On the other hand, if NQ is compact, right? These are positive operators. This guy is compact, and this guy is compact, and then therefore d bar star NQ is compact. So that's an easy but very useful reformulation. So now some examples. Well, one I've already mentioned. So I'll give you an example where we have compactness and then one where compactness fails. Well, in the strictly pseudoconvex case, it's one of the exercises to prove the estimate, the 1/2 norm here is less than or equal to square, well, it's some constant we don't care about. So then if we look at JQ, this embedding from domain D bar intersect domain D bar star into L2, this really factors through sub F 1/2, right? And sub F 1/2 into L2 is compact. And so JQ is compact, and we're done. Second example, let's take omega, the bidisk, sitting inside C2. This is pseudoconvex. This is not totally obvious from our definition of pseudoconvexity, but it is pseudoconvex. So I don't want to go into the details. Consider the following. And so let's take coordinates here, z and w. Consider the function, well, take f, a holomorphic function on the disk, and square integrable, so in the Bergman space. Consider the function w bar times f of c, I guess, and compute its t bar. Well, nothing when you hit the f, so it's just going to be f of c, and then the d bar of w bar is just going to be dw bar. Right? So i.e. w bar f of c solves, say, d bar h equals this form, f of c dw bar. And if f is square integrable on the disk, this is a form in L2 and so forth. So w bar f is a solution of this equation. I want to claim it's the canonical solution, that is the one that is orthogonal to holomorphic functions on the bidisk. So exercise. L2 omega, so orthogonal to the Bergman space. Because if you know that, then it's going to be the Kohn solution, the canonical solution. Well, why is that? Well, so you take the inner product of this, and then you get a holomorphic function here, barred. So you have w times this holomorphic function barred. If you do the integration, say, in the vertical, in the w direction, you get a multiple of the value at 0, right, just by the mean. But the value at 0, because the factor W is going to be 0. And so I guess I've done the exercise, right? Okay. So therefore, W bar F is D bar star N1 of the form F of C, dW bar. And I want to claim that D bar star N1, because of this, cannot be compact. And then a fortiori, N1's not going to be compact, right? If we can establish that. Well, proof. Well, so sort of indirect. So we have considered a map F goes to W bar F. Well, that's a composition. First F goes to this form. That's continuous in LD. And if this were compact, this would be compact, right? And that turns out to be a problem, namely, but I'm not going to compute the details, but it's not hard to check the norm of F on L2D is comparable to the norm of W bar F in L2 of the bidisk. So if this were to be compact, well, you do the identity and express it in sort of complicated way. Well, no, let me back up. I want to start that sentence again. So now, if you had a Gaussian sequence here, you'd have to have some convergent subsequence in the W bars F, right? But because the norms are comparable, you have a convergent subsequence back here. In other words, bounded sets in the Bergman space of the disk would be compact. Close to unit ball, the Bergman space of the disk would be compact. That is, it would be finite dimensional, which of course it is not.
So, F is a function already on the bidisk, is it?
No, it's just on the disk. It's just a function of C alone.
Oh, okay.
F is just a function of C alone.
One variable.
Yes. The other variable is W. But these norms here are comparable. It's just a little computation. And so if I take a bounded sequence here, this will be compact. The corresponding sequence multiplied with W bar would have a convergent subsequence, but that subsequence would also converge here because of this equivalence of the norms. So the unit ball in L2, well, in the holomorphic L2, in the Bergman space would be compact, and of course it's not, because that space is infinite dimensional. Okay. Well, so you could sort of try to see what the problem is with this domain. Well, it's D cross D, and so you have lots of analytic disks in the boundary, and these are definitely a problem. It turns out, at least for domains in C2, a single disk in the boundary will actually be an obstruction to compactness. We'll see that later on. All right. So now, I'm going to introduce a property which is of a potential theoretic nature. And sort of a priori, when I write it down, there's no reason why you would write this property down. But it turns out, I'll show that it does give a useful sufficient condition for compactness. And then we'll have to, the trick, of course, then is going to be to analyze this property to see what it really means, what it gives you. Well, actually, it's a little bit better. It's not totally out of the blue. Namely, it's called property PQ. We'll see why it's not totally out of the blue. This was done by Kathleen in about 84, and Sibony then was the one in an 87 paper in the Duke Journal who really analyzed this property sort of in the framework of Choquet theory. And that analysis is very useful. So, for all m positive, and the idea is m is going to be big, there exists a neighborhood U sub m of the boundary and a C2 function in U sub m. Well, let me give this function a name. Lambda sub m in U sub m, such that this function is between 0 and 1, and 2 for all C in U, the sum of the smallest Q eigenvalues of the complex Hessian is at least m. Now, the simplest case when Q is 1, this just says the smallest eigenvalue is at least m, or in other words, all the eigenvalues are at least m. Lambda m, I'm sorry. Yes. So it's in the beginning, it's useful to think about the case Q equals 1. So we just want these functions, if Q is 1, these functions then, of course, are plurals of Riemannic, right? Because the Hessian is in particular non-negative. So we want, for each m, want some little color, U sub m around the boundary, where the function is bounded. I mean, the 0 and 1 is not important by translating and scaling, but has big Hessian. Now, it's not totally out of the blue that this should be useful for compactness. If you recall, the estimate we have was the integral, and then there was the Hessian of a function applied to U, right? This was dominated by d bar U and d bar star U. If the Hessian is big, this says a big number times the norm of U, well, squared, actually, is dominated by d bar U squared, d bar star U squared. So if we divide by this big number, you get the 1 over m. That's going to be the epsilon in the lemma, in the proposition, rather, we had here. Epsilon's going to be 1 over, and then there's, of course, there are chunk terms around which are going to end up in there. So that's sort of the philosophy. Now, Kathleen introduced this condition for q equals 1, and it was in a context where for him it was actually natural to do that. It was finite type domains, and then he used the stratification of the V-close pseudoconvex boundary points to construct these functions. The correct formulation for q bigger than 1 is this one. Now, I said when q is 1, these functions are just plurisobharmonic. What are they when q is bigger than 1? Well, when q is bigger than 1, maybe we should write down this lemma now. When q is bigger than 1, these are functions which, on any affine subspace, any complex q-dimensional affine subspace, are plurisobharmonic. With, on the affine subspace, using the metric that's induced from Cn. You have to be careful because, right, the Laplacian is not, if you do something non-unitary, the Laplacian is going to change. So, take some function lambda that's C2, some open set U, then the following are equivalent. Sum of any q eigenvalues of d square lambda dCj dCk bar jk greater than or equal to 0. Well, here I'm saying any q, but that's the same as saying the sum of the smallest q, right? When you take the others, there'll still be similarly here. I could, instead of saying the smallest q eigenvalues, I could say the sum of any q eigenvalues is at least this. So this is if and only if f restricted to L is actually not plurisobharmonic, I'm sorry, subharmonic on every q-dimensional, well, on every L, which is a q-dimensional affine subspace. And like I said, the metric on L, you take the one that comes from Cn. So when q is 1, you're subharmonic in every complex line. That's plurisobharmonic. When q is n, you're just subharmonic in the Euclidean sense. All right. Okay, but now the reason for studying this condition is because it implies compactness. Actually, let me leave this as part of the estimate here for a second. So theorem, theorem 5, I think it is, okay. Omega bounded. Pseudoconvex 1 less than or equal to q less than or equal to n. If B omega satisfies property PQ, then Q is compact. So I'm just going to give the slightest of indications of the proof, what I just said here. Remember, we have this formula, summation jk, integral over omega e. Well, I take my function b to be e to the lambda m minus 1, then e to the lambda m is at most e minus 1. So then, oh, it's not an exponent, I'm sorry. It's minus 1. So then b is going to be less than or equal to 0. So here I'm going to have e to the lambda m minus 1. That's not going to change the Hessian, right? I'm going to have d squared lambda m dcj dck bar. And let me just do q equals 1 here. So I don't have to write as much uj uk bar. Well, there's some constant here, but it's independent of everything, d bar u squared. Now, if I look at this integral just on the part of um with the intersection of omega, then this thing is going to dominate m times u squared on the rest is compactly supported terms, and those are benign because, again, this is on the handout. On a compact subset, you have estimates in sub F1 in terms of d bar and d bar star, and this then embeds compactly into L2. So you're compact there. So you only have to worry about this, and now m is big. If you take 1 over m, that's going to get you the epsilon. And then from the compactly supported stuff, you get some more contributions here, but you get some chunk stuff here. And that's it. But you see why it was important to have this estimate without conditions on the smoothness of the boundary. This was actually in Catlin's original work. This was not contained. He needed to assume that the boundary was, I believe, C2, but as we've seen, it's not really necessary, which is a nice state of affairs. Okay. Well, we're going to talk about analytic disks in the boundary. These also occurred. On a strictly pseudo-convex domain? Well, one way we have seen, we get compactness we get because we have the subelliptic estimate, right? But you are asking, how does it satisfy property P? Yes, that's a good question. Actually, it does. It satisfies property P1, and so PQ for all. And the reason is you can, it's not hard to check. A strictly pseudo-convex domain, you can take a defining function where the Hessian is strictly positive, not only on the complex tangent space, but on all vectors in Cn. So now, you take a big multiple of such a defining function, you'll get a big Hessian, and then you just stay close enough to the boundary to be between 0 and 1. Maybe you have to add 1. Right. Mm-hmm. But that's a good point. No, if it's not strictly pluricharmonic, you're not okay.
Because you want the sum to be.
Well, if it's not, to get to turn it into a defining function where the Hessian is positive on all vectors instead of just in the complex tangent space, you need the strict positivity on the complex tangent space. Otherwise, you cannot do that. For example, convex domains have plurisobharmonic defining functions, but they can have lots of flat areas, disks in the boundary. Okay, so analytic disks is just as yesterday this is just a map. I think I'm using psi, goes from D into the boundary while sitting, of course, in Cn, and so that this is holomorphic. And as usual, we will sort of abuse language when we say an analytic disk. Sometimes we mean this map, sometimes we mean the image, right? All right. Exercise. If B omega contains an analytic disk, it does not satisfy P1. It will come out, well, not today probably, but tomorrow. This will be a trivial consequence of sort of a general theory, but one can prove this from scratch, namely, oh yeah, I'm sorry, this should be an embedding. I mean, yeah, sure, derivative is never zero kind of thing, absolutely. So one can show this sort of by hand, namely, so here's the unit disk, right? So you have this psi, omega, and you have this disk. So now, if you take these plurisobharmonic functions associated with every m, right, you can pull this function lambda m back to here, and the upshot is that if the boundary were to satisfy P1, you will get the following on the unit disk. You will get subharmonic functions, even C2 up to the boundary, if you take a little smaller piece of the disk here and rescale. C2 up the boundary, plurisobharmonic function, C2 up the boundary, between 0 and 1, but with the Hessian, which is now the Laplacian, with the Laplacian as big as you want. That cannot happen. You can draw a picture to sort of convince yourself. If here's the disk, and this function needs to be between 0 and 1, it can't be arbitrarily convex up. Of course, this is not a proof, but this is kind of what happens. So it's one of the exercises in the handout to prove this from scratch. And I give a hint there how to go about this. One can use a certain auxiliary function that comes from a solution of an appropriate Dirichlet problem, and then exploit the Poisson formula, play around with it, and see that there's going to be an upper bound on the minimum of the Laplacian. Okay. Let me take a couple of minutes to do one more thing. So now, for now, X is just a compact subset. Typically, X is going to be the boundary of our domain, but for now, this is general. We denote by P, capital P sub Q of X, the closure in in Cx, in other words, the uniform closure on X of functions in PQ of U in some neighborhood or for neighborhood U inside which exists. And his neighborhood is allowed to depend on the function. I mean, these functions, the PQ functions are, these are these guys. I should have said that. So there's C2, and they're subharmonic on any q-dimensional affine slice, or in terms of their Hessians, the sum of q eigenvalues is non-negative. And I mean, you take the closure, and then whatever you get, that's what we want. And it turns out, of course, the functions, the PQU, I mean, that's a Kohn. That is, if you add two functions there, you stay in there. Right? If you look on a slice, you stay. And if you multiply by a positive number, you stay in there. And so this PQ of X is a Kohn, and one can apply ideas of Choquet theory to this Kohn, and this is what Sibony did. One needs here the notion of Jensen measures, a q-Jensen measure. Mu should be a probability measure. On X, or well, so mu is a probability, U a probability measure on X is a q-Jensen measure for a point C in X if h of c less than or equal to integral over X, h d mu for all h in PQ of X. So in other words, a q-Jensen measure for a point, or there are those measures with respect to which PQ functions subaverage at C. And what we're going to be interested in is the set of those points where the only Jensen measure is the point mass at the point. This is going to be capital JQ of X. These are the points in X. Delta C, this means the point mass at C. Well, this should be C. The point mass at C is the only q-Jensen measure for C. This is also called the Choquet boundary. Of X. Well, with respect, of course, have to say with respect to which Kohn, to PQ of X. Okay. So that's as far as I'm going to go today. We will see first thing tomorrow that with this setup, we can characterize when a set X satisfies property PQ, namely, this will happen if and only if the Choquet boundary is all of X. That is, if and only if every point has the property that the point mass is the only Jensen measure. All right, thank you.
So, today there will be a photo taken right after this.